In this video, we're going to start looking at alkenes, which are a class of hydrocarbon related to alkanes, but with a slight difference. So first of all, notice that the suffix ene is now different. So alkenes are unsaturated, hydrocarbons. This word unsaturated, well, if you contrast it with the word we use for alkane, we said that alkanes were saturated, and we said that that meant had maximum number of hydrogen. Unsaturated means less than the maximum number of hydrogen. So less than maximum number of hydrogen atoms. Hydrocarbon, remember, just means contains carbon and hydrogen only. Now, because we've got less than the maximum number, rather than bond to hydrogen, we've obviously bonded to something else. And if there's only carbon and hydrogen, we must have bonded multiple bonds between carbon. So we've actually got double bonds. You can have triple bonds as well in unsaturated hydrocarbons. Those chemicals will be called alkynes, A-L-K-Y-N-E. Alkynes don't play a major role. Well, to my knowledge, they don't play any role metabolically. Structurally, perhaps, but not metabolically. So I won't feature them in this sequence of videos for a GOB class. We'll just stick with this as our representation of, for the most part, of unsaturated hydrocarbons. So we've got a double CC bond. An example, well, if I need double bonds, I clearly can't have methene because meth means one carbon. I need at least two, so the smallest alkene I could start with is ethene. So if I had two carbons, I could call this ethene. Notice that each carbon has 4 bonds total. It's got 2 singles and a double. I could have propene. Okay, so again, what they have in common is this double bond. You don't need all double bonds between your carbons. In fact, you couldn't have that. But you need at least one double bond to be classified overall as an alkene. If we were to, so I think what I'll probably do is I'll clear this board and we'll look at the condensed structure, the full structure, the skeletal structure, that type of thing, and then we'll get on to some nomenclature. So I'll tidy this board up a bit. Okay, so tidied up the board a little bit, and now we have some structures, some full structures of alkenes. Let's go ahead, name them, and we'll produce the condensed structure, the geometry, and the skeletal structure. So here I've got a full structure. Everything is exposed in terms of bonds and elements. coming in from the left and reading it, you've got a carbon with 2 H's. Then you have another carbon with 2 H's. The geometry of this, so what would it look like really? Well, double bonds can't twist. Double bonds can't twist. They're rigid structures for reasons that would go beyond this level, of course, to explain. But essentially, the pi bonding won't allow them to twist. So we'd have to draw them pretty rigid. And they actually, despite the way I've drawn them in the full structure, they actually have, around the carbon, they have a 120-degree bond angle. It's a linear, sorry, not a linear, it's a planar structure, but we'd at least have to represent the correct bond angle. So this might be how you put it on a piece of paper for full structure. You could also write this immediately. I tried to deliberately make mine look different so that I didn't just consistently write the geometry everywhere. But this would definitely be more accurate geometrically. Skeletal structure, remember we're just looking at carbons as dots. Lines between carbons are a bond, so 2 lines between carbons is a double bond. And we want to try and keep the honeycomb structure as much as we can. So I would just do that. So if you imagine a hexagon, so really anywhere on this hexagon you could have drawn your double bond. I could have drawn it here, which I did. I could have drawn it here, which I did not. I could have drawn it here, which I did not, etc. But you want to try and be consistent with this hexagonal type scaffolding. Okay, so this is ethene. Let's move on to propene. Okay, so we have, if we come in from the left, the way I've drawn it here, we have CH2, then we have CH, and then finally we have CH3. Okay, there's no other way, so this would tell a chemist that there must be a double bond there, because otherwise you'd need an extra hydrogen, so I've got less than the maximum number of hydrogen. If I were to look at the geometry, again, I would look for the longest, just like I did here, look for the longest continuous chain. And on this occasion, the longest continuous chain must include the double bond. So you can't have a longest continuous chain elsewhere without the double bond. If you have one double bond at least, that double bond must be in your longest chain because it's the new dominant feature. So I'll be consistent with this, so I will have those carbons, and then actually, yeah, this is the way most people would do it. I'll introduce a caveat in a second. Okay, so I've got my 2 H's here. I've got my H over here. Remember now I'm looking at 120-degree bond angle. And I've got my C. And then at this point you just want to keep everything 90 degrees if you can. Okay. You can always, with the geometry, because this is a 120-degree bond angle, which is the same as the honeycomb, you could always try and make it look like the honeycomb, but there's really no need at this stage. There's only really a need for the honeycomb in the skeletal structure. So that would be my skeletal structure. Again, I'm just focused on the carbons. I've got a double bond, a single bond, and I'm following the motif of a hexagon. So that's propene. here I've got, now if you look at these two, they both contain 4 carbons, but on the first example, I have the double bond between carbons 1 and 2, and in the second example, I have the double bond between carbons 2 and 3. So therefore, there's going to be a richer need for naming, or our language has to incorporate the apparent subjectivity of where this double bond is now. Because I can no longer just say butene, because but means 4 carbon, ene is a double bond. Well, that would be butene, but that would also be butene, but they're different. So this is the start of something that we're going to have to introduce, or at least the seeds, the foreshadowing seeds of complexity. So you want to tell people where the double bond is. So you want to, just as we did with alkane nomenclature, you want to alert people the location of the double bond. It's going to be between 2 carbons, and you only need to specify one of the carbons, and it was chosen that you'd specify the lowest number. So if I want that double bond to have the lowest possible numbers, because I'm going to prioritize it like a bud in a way, so I would number that 1, 2, 3, 4. With this structure here, it doesn't matter which way you number it because the double bond's in the middle. So I'll go ahead and number it this way. So in this double bond, I know it's butene, but I have to tell people where the ene is. It's between carbons 1 and 2. Well, I don't need to say between carbon 1 and 2. If we all agree that I'll just give you one of the numbers and we agree that it's the lowest one, then there's clarity of communication. So if I call this 1 butene, I'm telling you it's between carbons 1 and 2. Here, I want to tell you that it's between carbons 2 and 3. I just give the lower of the 2 numbers, 2 butene. Now, if you're watching this video in Europe, they tend to put the number between the branch and the suffix. So in Europe, you would more likely call this but2ene and but1ene. In the US, for whatever reason, they tend to put the number out, so it would be 1 butene rather than but1ene. Personally, I tend to prefer it this way, just because why chop up words with a number right in the middle? It seems more appropriate to keep the numbers separate. But don't be shocked if you research something and you see the number smack in the middle here. That's just a continental preference. Okay. Coming in from the left as written, we have CH2, CH, CH2, CH3, and here we have CH3, CH, and then another CH, and then finally a CH3. If we look at the top one, and we wanted to draw the geometry, we could have the double bond. Now, here's where I'm going to slightly deviate. So again, because it's going to be 120-degree bond angles, and just because I'm writing horizontally, I'm going to deliberately now use the honeycomb just so I don't have something taking up so many lines. So if I start off, so the only thing that matters here is the bond angle. So long as I make an effort to keep that 120-degree bond angle, I should be okay. So here's my first carbon with the 2 H's. Then I've got another H, and then I've got another 2 carbons. So I can do this. that will then afford me less space used on my board, if nothing else. Okay. But what I did overlook is my line wedge from another video. So I almost overlooked that. I'm glad I caught it. We know that we have to look at bond angles here. So from a previous video, we said that carbons with 4 single bonds, when read counterclockwise, would be line, line, wedge, dash. This has a 109.5 degree bond angle, which is in another video. But here, I have to acknowledge that this carbon has 4 bonds, and I almost missed it. So reading counterclockwise, line, line, so I need a wedge and a dash. And I've got 2 of them here, don't I? So let's go ahead and correct that real quick. Okay, so I've got my longest chain, and then on this carbon, I've got line, line, wedge, dash. And on this carbon, line, line, wedge, dash for these 2 carbons here. If I went ahead and looked at the skeletal structure, it would just be like this. So as you can see, a lot more efficient to draw the skeletal structure. This is all an organic chemist would rarely draw. They wouldn't bother with all of this unless somebody wanted, you know, hey, can you just remind me what that wedge diagram looked like? But usually we communicate just using this language here. Okay, and then finally for 2-butene, let's go ahead and start again. I'm just going to move the double bond between these locations. Around this carbon, I've got line, line, wedge, dash. And this carbon, I just have the 1 hydrogen. This carbon, the 1 hydrogen. This carbon, line, line, wedge, dash. For my 2-butene. And now if I did my skeletal structure, I have double bond that way, single bond that way, and single bond that way. Okay, one thing we haven't mentioned yet in this video is the formula that all alkanes have to follow. So the formula that the alkanes follow is CnH2n. So this is to be compared and contrasted with alkanes, where we said previously that alkanes follow CnH2n plus 2. Here the alkenes have CnH2n. So this is the basic premise. There is going to be an added bit of complexity when we look at cis-trans isomerization, but we're not there yet. There's no need to push into that yet. But at least we've seen, again, we've impressed in this video the efficiency of the skeletal structures compared to the other structures. Okay, in this continuation on this board, we're going to look at alkenes. Given a structure, we're going to produce the name, and then we're going to go back and forth, given the name, go back to the structure. Just out of convenience, I'm going to start immediately with the skeletal structure just because it communicates everything. We've seen skeletal structures now. And essentially, once you're comfortable with skeletal structures, you'll wonder why you didn't learn them sooner. So I've picked these four molecules deliberately. You can see here that everything looks the same between these two, although the double bond has migrated slightly. And the difference between these two, it seems that, now remember, double bonds can't twist, so I won't say twist, but it looks like this single bond is being broken and reattached in a different location. So these four structures will allow us not only to name and see some strategies for naming, but also, well, the last two are going to help us look at something called cis-trans isomers, or cis-trans isomerization. Okay, so the name of the game here is to identify the longest continuous carbon chain, but now it must contain the double bond, both carbons of the double bond. Okay, so it looks like I have 1, 2, 3, 4, and then any one of these could be the fifth one. So my longest continuous chain definitely has 5 carbons. So I know the 5 carbons are pentene. So 5 carbons is pent. It's an alkene, so it has the suffix -ene. And then I've got buds. Bud, bud, bud. This is a methyl bud, because there's 1 carbon in it. Methyl, methyl. So I've got 3 methyl buds. So trimethyl. All one word, trimethylpentene. Where are the methyl buds? Well, the dominant feature in an alkene is its double bond, so we want to give the double bond the lowest 2 numbers we can. So that means we would start counting this way. So I've got 1, 2, 3, 4, 5. And the convention is you don't need to specify both numbers, you just have to specify one of them, and I have just missed something out. So that is a good catch. I'd rather not miss it, but I've realized I've missed something. Okay, so let's go back. Before I think I got sidetracked with the buds too prematurely, which happens. So ignore the buds for now. We just want to really properly name the branch. So it's 1-pentene. We have to let folks know where the double bond is. So it's 5 carbons, there's a double bond, and if I put the number 1, I'm telling you it's between carbons 1 and 2. Okay, so correction, 1-pentene. Now let's go back. Trimethyl. So here, trimethyl is all one word, hyphen, 1, hyphen, pentene. I need to say where the 3 methyls are. The 3 methyls are on carbons 3 and 5. So there's 3, 5, 5. Tri means 3, so I need 3 numbers. They're on carbons 3, 5, and 5. So the complete name is 3,5,5-trimethyl-1-pentene. If I were given the name and I had to reproduce the structure, I would just say, okay, 5 carbons with a double bond between carbons 1 and 2. Number them 1, 2, 3, 4, 5. Carbon 3, 5, and 5, 3 methyls. And you'd have that structure. which that is not what I have done. Okay. Okay. So notice that this is a teachable moment. Notice that that structure is not the same as this. That's because I've named it incorrectly. I've named it incorrectly. Because did you notice that had 6 carbons? I've named it incorrectly. Look what I've done. Those methyl buds are on carbon 4. So making all kinds of teachable moment experiences today. Okay. Again, if you want to catch a mistake like I just did, take structure name, try and reverse again, and if you get something different, alarm bell should ring. I misnamed it. My buds were on carbon 4. Alright, now let's try and reproduce the correct name. Pentene. 1 pentene. 1, 2, 3, 4, 5. Okay. Methyl bud on carbons 3 and 4, so let's number them. Carbon 3, methyl bud, carbon 4, 2 methyl buds. Now we have the right structure. Okay, moving on. Looking for my longest continuous chain that contains the double bond. It looks like it's this one. So we want to prioritize the double bonds, so it seems to be closer to this end. So 1, 2, 3, 4, 5. The double bond is between carbons 2 and 3. So we've got 2 pentene. So instead of between carbons 1 and 2, it's between carbons 2 and 3. And then I have buds. I have a methyl bud. Another methyl bud. And a third methyl bud. Okay. So I have trimethyl again. Trimethyl is all one word. And this time the methyls are on carbons 3 and 4 again, exactly as they were. So 3, 4, 4. Separate numbers by commas, separate numbers and words by hyphens. Notice that the only thing that changed was the location of the double bond. So my final name is 3,4,4 trimethyl 2-pentene. Let's go ahead and see if we can get the structure from the name. So 2-pentene, 5 carbons, double bond between carbons 2 and 3. Number them. 1, 2, 3, 4, 5. On carbon 3, I have a methyl. And on carbon 4, I have 2 methyls. So that we have our skeletal constructed back again from the nomenclature or the name. These two structures, notice one of them is a cupped shape. So this top one here looks like a cup where my finger and my thumb are together. Whereas this one looks like almost like a chair. It's elongated. But otherwise, we have the same length branch. So our branch here is budless. So we'll do both of these in tandem. Our branch is budless, so we just have, and the double bonds in exactly the same location, and they can't become each other because double bonds can't twist. So these are two unique structures. So we have, if I number this, 1, 2, 3, 4, 1, 2, 3, 4. I definitely have 2 butene in both cases. Okay, 4 carbons, double bond between carbons 2 and 3, but yet they're still different. There's still something about them that's different. The difference is something we haven't looked at yet. It's called, they are essentially different shapes, and the way that we designate that difference is we say they are stereoisomers of each other. Stereo refers to shape. Isomer is essentially the same stuff, but in a different, something's different. Something's the same, the number of carbons and hydrogens and what have you. But something is different here, the shape. So the stereoisomers. So let's have, and I'll do a separate video on stereoisomers. We can write the word here for now, I guess. So these are stereoisomers. But again, I'll do a separate video on stereoisomers. So it looks like these two methyls are together on the same side of the double bond. If I were to look at the double bond axis, so let's redraw this a little bit. Typically we don't bother drawing the hydrogens, but let's do it on this occasion. Let's put the hydrogens back in. So it looks like I've got 2 methyl groups close together and 2 hydrogens close together. So if I were to look at the double bond in the axis of the double bond, then the methyls are together. So we represent the word together as cis. So we would call this cis-2-butene, where cis just means together. So this is a stereoisomer called cis-2-butene. If we look at this structure here, it looks like the methyls are across the double bond. Again, if we were to look at the axis of that double bond, I've got a methyl below it and a methyl above it. Previously, they were both the same side, but here we've got different sides of the double bond. So we call this trans. Trans is a much more self-intuitive word. Trans means across or opposite. You know, if you take a transcontinental flight, you go across a continent. Translation, the word trans is used a lot more ubiquitously in language. So we've got this extra feature now in our naming. We've got cis and trans. So we've actually got, if I erase this a little bit, we've started to see cis trans isomers. Cis-trans isomers requires a double bond. You would never have a cis-trans isomer in an alkane, for example, because alkanes only have single bonds can twist. If this were a single bond, it would be exactly the same chemical. It's only because of the rigid nature of the double bond, the lack of twistability of a double bond, that gives rise to this difference, permanent difference in these molecules. So cis-trans isomers applies only to alkenes. There are lots of alkenes in biology, biology makes extensive use of alkene chemistry, so there's lots of cis-trans isomers in biology in this type of course, this GOB chemistry course. Cis-trans isomers are a type of stereoisomer. Where here stereo is concerned with the shape. So shape similarities and shape differences, this is something to look out for. Although cis-trans isomers apply to alkenes, not all alkenes need cis and trans. Let's look at just one quick example of an alkene that doesn't have cis-trans isomers. In fact, I'll pause it, I'll clean this board up. We'll just conclude this video by looking at some examples of alkenes where there's no mention of cis-trans isomers. So let's look at these two structures here, which we'll see if the cis-trans isomers apply to this structure. Okay, so if we look across the double bond, so let's redraw. We've got that double bond, and then it looks like we have methyls above and below. Okay, looks like we have methyls above and below. Clearly, if we look at the axis of the double bond, there's a symmetry. So you could say that these two methyls are trans, but these two methyls are cis. So it's kind of neither nor. So there's no evidence of cis-trans isomerization going on here. So we don't need the labels, we don't need the prefixes cis or trans in the structure. So let's go ahead and name. Longest continuous chain that houses the double bond has 4 carbons. So we know it's butene. The double bond is between carbons 2 and 3. So we've got methyl buds. Double bond is between carbons 2 and 3, so we just cite the lower of the two numbers, 2-butene. We've got methyl buds on carbons 2 and 3. So it's dimethyl and they are on carbons 2 and 3. So the final name for this structure is 2,3-dimethyl-2-butene. Again, if you needed to re-engineer this structure, you would just have 2-butene. Number it 1, 2, 3, 4. On carbons 2 and 3, you'd have 2 methyls. And you'd regenerate the original structure. So no evidence of isomerization here. In this structure, we don't have symmetry about the double bond. We don't have symmetry about the double bond. If I look down the axis of this structure, I have 2 methyls below, but I have a methyl and an ethyl above. So I definitely have some asymmetry. But do I have cis-trans isomerization? Well, let's see. Let's look at the longest continuous chain, which is clearly that contains the double bond. And I have 1, 2, 3, 4, 5 carbons in that continuous chain. So that would be pentene. The double bond is between, well, it has to be the lowest possible numbers. So it's closer to this bottom end. So 1, 2, 3, 4, 5. It's between carbons 2 and 3, so I just cite the lower number, 2-pentene. So 2-pentene. I clearly see now I have 2 buds, 2 methyl buds. I have a bud on carbon 2 and 3, so I have dimethyl. And they're on carbons 2 and 3 respectively. So this structure is explained perfectly well, no need for cis-trans isomerization. It's explained as 2,3-dimethyl 2-pentene. Well, what if I drew, you might be wondering, what if I ripped one of these bonds off and reattached it down here? What if I had this down here? Remember, you can't twist, so I wouldn't accuse you of saying twist. But it's not accusatory to suggest that you might say remove and reattach. Well, they're just identical structures, aren't they? You know, if I were to rotate this again without doing anything to it, I could reproduce this without breaking anything, without attempting to do the forbidden twisting of anything. So these are just identical. One go-to way I would give you to ascertain whether, or one feature that you would look for if you want to see if you have cis-trans isomers, is you want to look at one of the carbons. If any one of these double bond carbons has 2 identical groups on it, like we do here, then cis-trans isomers are impossible. So even though they're different, they're the same. So that type of isomerization is off the table. Okay, so we'll clear up this board.